This series of 2 talks will be on multidimensional and nonlinear mechanism design, and I'll give some application to approximation at various points in the talk as well. Today I'm going to focus on one perspective you can take on this problem, which is to understand the problem modularly. In other words, how do you construct multiplayer auctions from single-player auctions? Okay, and so it's going to focus on multi to single agent reductions and what we can learn about the structure of good mechanisms from the way that the multiplayer mechanisms interact with the single-player mechanisms. This is Chapter 8 of a textbook manuscript that I'm currently working on. Any decade now, it should be ready. Chapter 8 was something I've been working intensively on this summer, which is why it's very fresh in my mind. It's something I wanted to share with you, this sort of unified way to think about these kinds of questions. Unfortunately, Chapter 8 is actually not quite ready yet, so it's coming soon on the web page here if you're looking for notes for later. Okay, so I want to start out by giving you some results that will be consequences of the theory I'm going to develop, so you can see what we're working towards. Okay, and what I wanted, the entire, most of this talk will be, and today and even tomorrow, will be trying to draw connections between the multidimensional nonlinear setting of mechanism design, which is, I guess, not as well understood as the simpler single-dimensional linear settings that the classical economic theory has described. And so in order to understand these more complex mechanisms, I'm actually going to try to understand them in the same terms as we understood the single-dimensional linear agent case, which is fairly easy to understand. And so I'm going to be drawing those connections throughout the presentations. So I want you to compare these results to similar results you know from the single-dimensional theory. Okay, so here's one result. Suppose you have a multi-dimensional agent. In particular, you could be selling a car that you could paint either red or blue. And the agents might have a different value for different colors you could paint it. Okay, and so if you imagine that the values for the colors are drawn IID from each player's IID on the uniform square for their value for blue or red, then the following auction is optimal. Just run the second price auction with a reserve and always sell the person who wins their favorite color car. Okay, and that should look a lot like, wow, I misspelled Meyerson's name. That should look a lot like the single-dimensional theory, which you're familiar, where the optimal auction for single-dimensional linear agents with IID players with a nice distribution is the second price auction with reserve. Here's another result, for this time for nonlinear agents. If you're selling a single item to agents with values uniform 0, 1, and they have a common budget, so there's a maximum they can pay, and that's the same maximum for everybody. Okay, so it's a symmetric environment. Okay, then the optimal auction is actually also relatively simple. It's an all-pay auction with a reserve price, meaning people who aren't willing to bid a certain amount aren't even considered. But there'll be what we'll call ironing at the top, meaning there's the high-valued agents will all bid the same amount. And if there are more than one that bid that amount, you'll pick a random one to win. So it'll be basically ironed. Okay? I put ironing at the top in parentheses because when you actually implement this, you don't need to actually iron at the top. The agents will do it for you. Okay? You just run the all-pay auction with a reserve. They're not going to pay more than their budget, so they'll all automatically iron themselves in the correct way. Okay, I'm going to, this theorem is actually Lafont and Robert, but I'm going to give you a proof of this theorem which follows much more closely the Bulow-Roberts marginal revenue approach. Okay, so these are some results for optimal mechanisms with multidimensional and nonlinear preferences. I now want to tell you how, because we've viewed these similarly to the single-dimensional settings we know, we can automatically get approximation results that are related. Okay, so in the multidimensional setting, you can automatically get these kinds of approximation results. If I just post a uniform price for these IID agents, then I'm going to guarantee an E over E minus 1, which is 1.58, which is the same as 1 over 0.63 that Tim was talking about the other day, approximation. Okay, and this is via a correlation gap result of Yan in the single-dimensional setting, and it automatically extends to this multidimensional setting because we're going to have viewed it in the same, using the same working pieces as the single-dimensional linear case. Okay. Similarly, a recent result with some co-authors who Said is actually around in this area and will be probably spending some time here in this special semester, is that even if you have asymmetric distributions, so imagine here we have uniform 0, 1, and they're all IID. But imagine everyone's uniform 0, some upper bound, but the upper bounds are different for different players. So now we have an asymmetric setting. Okay? And so the optimal auction there, like this one, is going to be basically look like a highest virtual bid wins kind of a thing, and the same as the single-dimensional setting. But that auction's not so practical. So you might wonder, can you get away with just posting a uniform price that's anonymous to everybody? How well does that do? And in fact, the same question was wondered for single-dimensional linear agents, and it was proved in these papers. And that theorem automatically extends. Okay, an extension for this result with common budgets is that, well, if you have a lot of players, you don't even need a reserve. Okay, it's sort of extending the Bülow-Klemperer result to this setting. Because we viewed it in the marginal revenue framework to prove this theorem, we can use that same viewpoint where there's a sort of marginal revenue version of the Bülow-Klemperer theorem to show that the all-pay auction with no reserve is a good approximation to the optimal one. Okay. Good. So this is sort of to motivate what we're doing. We're going to try to understand optimal auctions in the same terms in which we understood the single-dimensional linear case, these much more complicated cases of multi-dimensional players or nonlinear players. And because we did that, we'll get for free a lot of extension theorems where you'll see the single-dimensional results will automatically extend to the more complex environment. Okay, so I'm going to be talking about multi to single agent reductions. I'm going to give you 2 reductions, and they're going to work in different cases. Okay, the first and easier reduction I'm going to call the ex ante reduction. And I'm going to reduce the multiplayer problem to an ex ante pricing problem for the individual agents. And what is that ex ante pricing problem? I'm going to look at each single agent and ask for any probability that I serve them, what is the best mechanism that serves them with that ex ante probability? Okay? If you solve this problem for every ex ante probability, then we'll be able to construct a mechanism from those single player mechanisms. Okay? And the multi-agent composition mechanism will be the marginal revenue mechanism that you may be familiar with from Bülow and Roberts. Okay? This approach does not always work. It will work if and only if the single agent problems satisfy a property which I'll call revenue linearity, and we'll discuss in more detail later. Okay? But in particular, there are 2 common cases that you might think about that satisfy this revenue linearity assumption. One is the standard single-dimensional linear utility preferences that we're used to talking about in auction theory from Meyerson's theory. And another case is a large class of multidimensional preferences, which I'll talk in much more detail about tomorrow. Okay, it includes the uniform 0, 1 squared example of the red-blue car that I just was talking about. Okay, and so that theorem on the previous slide is just an instantiation of this reduction and its optimality. Okay, The other reduction is, I'll call the interim reduction, and it's based on interim allocation rules of the players, and in fact solving an optimization problem that has the interim allocation rule constrained everywhere. Okay, so the single agent problem is a constraint on the entire allocation rule, not just the ex ante probability of service. Okay, and the multi-agent composition mechanism is going to look like a stochastic weighted optimization. Okay, and I don't want to go into more detail about what this is now. We'll talk in much more detail later. One point is this is a much more complicated procedure. This is more complicated, and also this is more complicated. There are no assumptions you make on the preferences here to do this. So the multi-dimensional settings that you can't solve because they're not revenue linear, you can solve here with this approach. And you can also solve nonlinear utility preferences, either single or multi-dimensional, doesn't matter. Okay. Examples of nonlinear preferences are budgets like I had in the previous slide, or risk aversion. Okay, and the example theorem from the previous slide about the optimal auction for budgets is instantiating this framework in a symmetric environment where actually there's some simplification you can do to make this not so complex. Okay, so what's my agenda? My goal really is to have you understand what these reductions look like, have some intuition for them, and understand what's fundamentally different about the settings where you can use one or the other. Okay, that's my goal. Okay, so I'm going to start with some examples of optimal single agent mechanisms so you can see already that the single agent mechanisms for the two cases, the revenue linear case and the non-revenue linear case, are behaving very differently. Okay? And then, once we see them behaving very differently, we will construct the ex ante reduction and prove its correctness, and then we'll construct the interim reduction and prove its correctness. Again, the things I want you to think about here, this is a unified framework for thinking about mechanism design. And I really want to highlight the differences between the revenue linear case, where basically Meyerson-Bulow-Roberts theorem extends, to the non-revenue linear case, where it doesn't and have to use more sophisticated methods. Okay. So I'm going to now work through some examples of some single agent mechanisms. Please feel free to interrupt if you have questions and want to clarify what these examples are. Okay, so I'm going to start with the public budget preference. So here's just a simple public budget preference, which is the same example I had in the first slide. So I have an agent with a private value T for receiving some good. I can give them the good with some probability, X, and charge them some payment P. Okay? They have a public budget, and so their utility function is this. They get utility T times X minus P. That's your usual quasi-linear utility, except that requires that the payment be at most the budget. If the payment is bigger than the budget, they have negative infinity utility. Okay, this is a somewhat standard model for thinking about budgets. Okay, I'm going to use as a running example for everything I show you in this talk will be for T is uniform 0, 1, and the budget is a quarter. Okay, and every picture is a real picture. Meaning it actually corresponds to, when I show you an optimal auction, it's that case, the uniform 0, 1, budget a quarter. Okay, whereas the theorems will actually be more general than this case, but I'm not going to show you the more general picture, even though it's going to be just an obvious extrapolation. Yeah?
I know this minus infinity is completely standard, but would it be good enough really to do minus the loss? You know, so if you are seeking...
I have no idea. I have no idea. Okay, so I want to start by talking about some ex-ante pricing mechanisms, meaning in a second we're going to want to optimize, given some constraint on the ex-ante probability I serve a player, what is the revenue optimal mechanism for that constraint. So let's just look at a couple mechanisms that satisfy some constraint. Okay, so I'm going to start with an ex-ante constraint of 1/2. So meaning come up with a mechanism which serves the agent with ex-ante probability 1/2. The mechanism may randomize, and the type of the player is random. And so it's going to be serving with probably 1/2 in both the randomization of the mechanism and the type of the player. Okay, so here is one mechanism. I could offer the player a 3/4 lottery, meaning X is 3/4, and charge them, if they want to buy that lottery, 1/4. Remember, they have a budget of 1/4, so that's a binding budget constraint for them. Okay, and if they don't want that, they can have nothing. So what does this do? Well, you can solve for what is the indifferent type, the type that doesn't care if they buy this or not buy this, by saying, OK, what type has t times x minus p, which is 3/4 equal to 0? T times 1/4 times, and it's exactly the type of 1/3. OK? So the allocation rule looks like this. The types with type below 1/3 don't buy. The types above 1/3 buy, but they only buy with probably 3/4 because it's a 3/4 lottery. Okay, and as usual, if you're used to thinking about single-dimensional auction theory, the payment in an auction, if I write the allocation rule in type space like this, is just the area above the curve. So the shaded area that I've denoted B is actually the payment that the high type makes, which is equal to the budget, which is a binding budget constraint. Here is another example. I want to tell you where this example comes from. Let's suppose I ran a 2-player all-pay auction for players of this type and asked what the equilibrium was. That equilibrium produces an allocation rule. It happens to be this. Okay, what's going on here? I started with highest bid wins, right? But if I just run highest bid wins, the top guys are going to overspend their budget. So they want to lower. They want to pool themselves with lower types. Okay, but if the top players start pooling themselves, then some of the lower players are going to also want to pool, because then they get, they win with some higher probability because they get a chance at winning when they're pooled with the high types too. So the high types drop down, some low types drop up, and you get the lowest type that's indifferent between dropping up is this guy, everyone else is as before, and these guys are all pooled. Okay, and you can calculate out the area of this B. It's exactly 1/4 as before, and you could calculate out the probability of the ex-ante probability, and it's also 1/2 as I desired. Okay, these are two mechanisms. Good. Let's think about this ex-ante pricing question. I want to come up with the single-player mechanism that has the highest revenue, but serves with the ex-ante probability, say at most 1/2. What is that? Give you a hint. It's one of these. Which one?
Biggest area?
The biggest area. So the B's are both the same for them, right? So the question, right? The thing is that everyone here who wins pays B. And here, some of the people pay some lower amount because the guy with the type here pays the area above the curve for that type. Right? So here, we sell with probably 1/4 and everyone pays B. Here we sell with probably, 1/2 and everyone pays B. Here we sell with probably 1/2, but some people don't pay B. Does that make it easier? Which one's bigger? Okay, and in fact, A is optimal. Okay, and in fact, the theorem you can show is that a mechanism of this form is optimal. And what is all I want you to get from this is the following: is that the probability of the lottery, which was 3/4 here, changes with your ex-ante probability. Okay, so you're taking this curve and squunching it down as you change the probabilities. Okay. Any questions on this? We'll revisit the example further once we make it more complicated, but happy to.
So the mechanism.
By the way, I also did not tell you what happens when the budget's not binding. When the budget's not binding, it's obvious what happens. You just post a price. Okay, so this is the budget binding case here. And the budget's obviously not binding when this equation can't be satisfied by anything.
So the mechanism on the left was also for 2 agents, and
No. This is a single player question. This came from somewhere. I looked at what the interim allocation rule was for a 2-player mechanism, and this is what happens. Okay? This doesn't come from any 2-player mechanism that I ever thought of. It just happens to be a single player mechanism. You could post this lottery. What happens then? Okay, let's move on to unit demand preferences. Okay, so it should not say single dimensional there. Unit demand preferences, multidimensional. How am I going to notate this? Sorry, this notation is a little bit clunky. An allocation is going to be a probability of getting item alternative 1 or alternative 2. Okay. It better be that your unit demands, you only want one thing, so it better be that the total number of things you get is at most 1. Okay, and you'll have a payment P.
Sorry, Jason, I don't understand. X1 is the probability I get the first good.
X1 is the probability you get the first item.
Right.
X2 is the probability you get the second item.
So if X1 and X2 are both 0.9, I might get both items, but I might not get any items. So
You are thinking about these as independent random variables. They are not. These are the probability of getting, it's like the simplex. There are 2 outcomes. You get 1, 2, or 0, and it's a simplex, so it sums to at most 1.
Got it.
Okay? Your private value has 2 coordinates. Your utility is just the sum of your value for the things you get. Your standard linear utility definition. Okay? My running example is T is going to be uniform 0, 1 squared. Okay? I want to do the exact same thing we did before. I want to ask you what are some mechanisms that serve with ex ante probability Q hat for, say, Q hat equals 1/2. Okay, here's something you could do. Only ever sell item 1. If I want to sell with probability 1/2 and I only want to sell item 1, I better post a price of 1/2 the player's uniform 0, 1. Here's something else you could do.
Q hat here corresponds to x1 plus x2?
Q hat corresponds to the probability. Yeah, so the probability they buy anything in expectation over the types, and both could be random, the types and also the x's.
Right. But so either the first one or the second?
Yes, that's correct. And in fact, later I'll just say x to denote the sum of the 2. So I need x less than 1. Okay, so that's something I could do. I could also sell them the lottery, okay, and this would actually be a price 1/2. So at price 1/2, you can either get 50-50 of the first item or the second item. Okay, but so if you win with probability 1 though.
That's right. So what's the heading on this? So does this
Uniform lottery over items.
Does the right-hand example have Q hat equals 1/2 or Q hat equals 1? I was trying to.
They both have Q hat equals 1/2.
But the right-hand lottery, you're certain probably 1.
Except that you only have a high type with probably 1/2.
So you probably 1 conditional on
Exactly. In both of these, you're served with probably 1 condition on being served. Okay, but only some types will be served, and that types being served are the areas given by their shaded regions. Okay, here is another allocation rule. It's a uniform pricing of a price of square root 1/2. Why square root 1/2? Well, I want this area to be 1/2. I want this area to be 1/2, which is the same as this area being 1/2. And that area is 1/2 if my price is square root 1/2. Okay?
So, Jason, so this is for unit demand. So Q hat, the ex ante probability of service kind of makes sense. But say if it was additive, how would you define the ex ante probability?
I would have to define a different kind of ex-ante problem for additive if I had a feasibility constraint across the multiple agents that had the externality for the different items. So I'm going to be focusing today on settings where the externality between players is a single-dimensional externality. Okay, if you have a multi-dimensional externality between players, which is what Costas, I believe, is asking about, then you'll need to define a different ex-ante pricing problem. I'm not going to talk about that today. The different ex-ante pricing problem is actually in Saeed Alai's 2011 paper. Okay, so good. I have 3 mechanisms here. I'll give you a hint. One of them is optimal. Which one is it?
The one on the right, probably.
Yeah, so, wait, I called them all A.
You can spot somebody with jet lag.
Okay, so C is right. And if you remember the first slide, you should recognize C being the right answer. And in general, what's the right answer? It's going to be the uniform price that is calculated here. What is this max? This max is because actually when you have too high a probability, you actually don't want to sell with that total probability. So you're allowed to not sell with the total probability in the ex-ante pricing problem. Okay? So I want to post the price that corresponds to the price that has this area exactly equal to Q hat. Okay? But I don't want to go below square root 1/3, which is what this constraint is saying.
How do you tell from looking at the picture which is optimal?
You can't. In fact, no. So I want to remind you my agenda. My agenda is to give you examples of what optimal mechanisms look like in the single agent setting. I'm then going to talk about the reduction. We're focusing on how do we build optimal mechanisms from the single agent mechanisms, and knowing what the single agent mechanisms look like is going to help us do that. Tomorrow, I'm going to go and derive how to show that these are optimal. Okay? Good. Any other questions? Yeah.
I know this may be a silly question, but could you give some motivation as to why we would want, when are we given an exogenous probability that we want to select ex-ante with?
No, I won't, actually. And the reason why I won't is because I'm using it as a tool to build the optimal mechanism. Okay, so I don't actually care about that question in itself. Okay, I care about that question as a building block in constructing optimal multiplayer mechanisms. One of the reasons why I think this viewpoint as a reduction is so important is that if you look at some of the literature where people are studying single-player problems, they're not necessarily studying these ones. And they should be, because these are the ones from which you can construct multiplayer mechanisms. Okay, so that completes my survey by example of ex-ante pricings. Okay, I now want to talk about the more complicated single-player problem, which the second kind of reduction is going to use, which is interim pricings. Okay, so to do that, I'm going to have to introduce some notation for allocation rules, etc. Okay, so I'm going to define the allocation rule as for types to be x is just the probability that the type is served. And answering a previous question of Costas, that's going to be, in the unit demand case, it's the sum of the probabilities you get either item. It's the probability you get anything. Okay? So if you have a mechanism in mind, and we will usually have a mechanism in mind, then I can measure the relative strength of two different types of the players from the distribution by asking which one has a higher service probability in that mechanism. Okay? And I'm going to call the quantile of an agent Q to be the measure of types with higher allocation probability in the mechanism that we were thinking about. Okay, so given a mechanism, I look at all the allocation probabilities. What's the probability that a random type has a higher allocation probability than this type? That's the quantile of the type. Okay? And the important definition, the important property of quantiles is that for any type from the distribution, quantile is always uniform 0, 1. Because any ordering by strength will always give you an ordering 0, 1 when you look at the relative strength. Okay? So now I'm going to take my allocation rule in type space and define an allocation rule in quantile space. Okay? Which, if you had a mapping for types of quantiles, just maps them. Okay, but let's actually think about what that is. So the allocation rule in quantile space is if you take the allocation probabilities of the player of the types and you sort them in decreasing probability with widths equal to sort of the probability they show up, then you get this allocation rule in quantile space. Okay? For discrete type spaces, it's very intuitive. Okay? For discrete type spaces, make a rectangle with width the probability the type shows up and height the probability the type is served. You take those rectangles and you sort them in decreasing order, and the profile, the top profile, will be an allocation rule. Okay? This is the allocation rule in general for a mechanism in quantile space. Okay, let's do some examples. So public budgets, we saw this allocation rule before in type space. Types were just uniform 0, 1. So what is the allocation rule in quantile space? Well, you know, this measure 1/2 of types all get served with the highest probability, which is 3/4. So there's that big rectangle. And then these other infinitesimal agents get served with decreasing probability, and so they're just here. Okay, and actually for uniform 0, 1, it's just you just flip it. Okay.
What is F of t? Sorry.
F is the density function. Okay, so what about this unit demand example? What's the allocation rule here? Well, these types receive a good with certainty. What measure are there? There are 1/2 of them. These types receive the type not at all. So if I take the allocation rule and sort it and put it in probability space, then 1/2 measure get it with certainty, 1/2 measure get nothing. This is the allocation rule in quantile space. Okay, I now am ready to define this interim pricing problem. Okay, the interim pricing problem assumes that I'm given an allocation constraint y, which is the same form as an allocation rule in quantile space. Okay, I'm going to use hats, by the way, for constraints. Every time I have a constraint, I'll put a hat on it. Okay, so y is just a monotone decreasing function from 0, 1 to 0, 1, y hat. Okay, and what I would like you to do is come up with a stationary transformation from quantiles to quantiles, so from uniform from 0, 1 to 0, 1, that is stationary. So if I take a random quantile from uniform 0, 1 and I put it in my transformation, I get a random variable that's also uniform 0, 1. Okay?
So what does stationary mean? I don't know what stationary means in this context.
Good. So I'm going to put into sigma a quantile Q. That quantile Q is drawn from the uniform distribution. I would like the expected value of sigma Q, if I don't tell you Q, to also be from the uniform distribution. That's what I mean by stationary. It takes a distribution as input, and if that distribution is uniform, gives you the same distribution out. Yeah?
You want it only for the uniform distribution?
Only for the uniform distribution. Okay? I want you to find one of these sigmas. Okay? And then I want you to find me a single agent mechanism with allocation rule that is upper bounded by the expected allocation constraint when I remap things by sigma. Okay?
Any sigma? Every sigma?
No, you're finding both these things. So
wouldn't I take sigma as the identity?
Because if you take sigma's identity, you won't be able to come up with as good mechanisms as if you don't take sigma as the identity. Okay, that would constrain you artificially.
So is it a permutation? I'm trying to understand what's going on here.
I'll tell you one of the kinds of things you're going to want to do with sigma. You're going to want to take an interval between A and B, and you're going to want to just uniformly redraw it. So if I condition on a type being in some interval, quantile being in AB, and I ignore it, and I redraw a new type from that interval, what's the new distribution? It's still uniform 0, 1. Okay? That's how we're going to use sigma in constructions. I want to give you another way. If you find this definition confusing, I'm happy for you to take the theorem I'm going to prove as the definition instead. Okay, so let's define the cumulative allocation rule as just its integral. Okay, so the cumulative allocation rule for q hat is integrating the allocation rule from 0 to q hat. Okay, in other words, let's think about this. Q hat is a constraint on the quantile, right? So I take all the players with quantile stronger than q hat, and I ask what's their expected probability of being served. Okay. So the allocation rule y is feasible for allocation constraint y hat if and only if the cumulative allocation rules satisfy the pointwise domination condition. This is like basically asks for majorization, basically, if you want to think of it that way. Okay, it's like a majorization property. For those of you who know what that means.
So the definition of feasible is there exists sigma such that the second point holds?
Yes. So you'll say y is feasible if there exists sigma such that this is true. Okay. The theorem is that these are the same things. So if you found that definition confusing, you can just take this as the definition. Okay. In other words, it's a constraint on every prefix of strongest types of the ex ante probability you serve a type in that prefix. Okay. I want to actually prove this theorem by showing you how to construct the sigma that you want for this theorem. Okay? And the main idea is that if I take an allocation rule y and I use some sigma that resamples on some interval AB by ignoring the actual quantile that was in AB and drawing uniformly from AB instead, okay, that'll replace the allocation constraint y hat, little y hat, with its expectation, and that replaces the cumulative allocation rule with a line segment connecting the 2 points. Okay, so here are pictures. Okay, let's suppose my allocation constraint y hat is the straight line, the 45-degree line. And let's suppose the allocation rule y I want to implement is this stair function, the black stair function. And this violates Richard's property that it's always pointwise less than it. Okay? But we can actually implement this stair function from this allocation constraint y using such a sigma. Okay? How are we going to do it? The first thing I'm going to do is throw out probability to make the ex ante allocation probabilities the same. Notice that y, capital Y of 1 is just the total probability the guy served. Okay, so this point and this point, this is the ex ante probability of y hat. This is the ex ante probability of y. How can I make them the same? Well, if your type is, if you're in the weakest types here, I'll just set your y hat to 0. Okay, that would take this curve, which is still increasing, and make it flat. Okay, so that's how I go from the dotted line to this one truncated here. Then the next thing I want to do is use the fact that resampling on interval AB is replacing a line segment in the cumulative allocation rule. So if I want to take this curve, which goes like that, and make it look like this curve here, I can just take that interval and resample it. Okay? So I resample between 0 and this somewhere here. Okay? And then I get this dotted curve. Okay? And then I can resample on this interval to take that thing and flatten it to this line. Okay? That's the construction.
Can you motivate this a little bit? Like, where's this allocation constraint coming from?
Again, no, I don't want to motivate it. The same answer as before. I don't care about these problems. These problems are coming from a multi-agent reduction. I'm going to have to solve them. No, but it's good to remember that, so thanks for asking.
Just say it's going to be a separation oracle for something.
Okay, so I want to now look at example interim pricings. And my example is going to be for the allocation constraint y hat, this is the minus 45-degree line. It's the one we were talking about in the previous slide. Okay? So here I've shown the constraint with a dotted line. And I've shown what is the optimal allocation rule for the public budget example previously, given that allocation constraint. Okay, and what does it do? It irons the top, it reserve prices the bottom, and in some middle interval, it's greedy. It's the highest type wins. Or smallest quantile, the strongest quantile wins. Okay? And that corresponds back in type space to this allocation rule. Okay. Good. What about the unit demand case? Again, taking the exact same unit demand example, the allocation constraint y hat is the minus 45-degree line. The optimal allocation has this allocation rule here, just the reserve price. Greedy allocating by strongest quantile until the reserve price. And the mechanism in two-dimensional space looks like this. The reserve price, as I said before, is square root 1/3. And we'll allocate with increasing probability to the types as they get highest coordinate. Okay, so note these types are the ones where they prefer item 1. These are the types that prefer item 2. And we're allocating probability in terms of their highest coordinate. Okay, again, for this part of the talk, I don't need you to understand how to get this from the constraint or anything. I just want you to understand what these things look like. Okay, I want to point out something is quite different about these two scenarios, which I haven't written here in this slide. I'll just tell it to you. This, so I have written it here. So this reserve is the same reserve that you would get for every single allocation constraint y hat. Okay, for every single allocation constraint y hat, it would look, y would look exactly like y hat down to the quantile, the 2/3, which corresponds to a reserve of square root 1/3 in price space. Okay, that is not the same for the public budget example. These two thresholds, which one of them is where you iron and one of them is where you put the reserve price, these will be different for every allocation rule you choose. Okay? And the thing that's important about that is in the unit demand case, there's something that's sort of unchanging about your optimization problem. No matter what the constraint is, the problem is unchanging. Whereas for the public budget case, actually things are moving. You change your allocation rule, the things that were relevant before are no longer relevant. You have to think about other things. Yeah?
So I'm a little bit confused when you talk about changing your allocation rule versus changing y hat. I'm sort of thinking of y hat as this sort of exogenous, unmotivated thing that's coming from space.
Yeah.
And y is the thing we actually want to implement, right?
Yeah.
So can you clarify a little bit which?
Yeah. So I'm thinking about changing y hat and asking how the optimal mechanism changes and these things I need to know. So when I give you the y hat of 1 minus q, okay, meaning this one, I got these particular IR on the top and reserve price the bottom with these particular parameters. Those parameters depend on y hat. If I give you a different y hat, you get the exact same structural picture, IR on the top, reserve price the bottom, but the reserve price will be different and the ironing region will be different. Okay? That does not happen here. For every single y hat, you get the exact same reserve price. Okay? One thing we can point out from this previous slide is what was the optimal ex ante mechanisms for this problem? They were just posting a uniform price, right? What is this mechanism? It actually looks just like a convex combination of posting a uniform price for different probabilities of posting the price. Okay, so the interim optimal mechanism is going to be a convex combination of ex ante optimal mechanisms in the unit demand example. That's not true in the public budget example. Okay? Also, the ordering on types. So we said we defined, we said that for every mechanism, you could map types to quantiles by looking at the probability that the type wins in that mechanism. So for the unit demand example, for every single allocation constraint you give it, the same ordering is fine. Okay, the orderings are consistent. There's one ordering on types that's always the ordering. And in fact, that ordering is kind of obvious to see. You want to order them by their highest coordinate because that tells you when they're going to win or not, because they're all basically competing in this auction for who's got the highest favorite item. Okay, so I'm calling that second property orderability when every single agent interim mechanism has the same order on types. Okay, I'm going to define some notation. So if I give you a constraint y hat and I want you to optimize revenue subject to that interim constraint y hat, I'm going to denote that by rev of y hat as the optimal revenue I get for that constraint. Okay, then this revenue linearity property more formally is just the following. If I give you two allocation constraints that sum to be a third constraint, then the revenue is just the sum. The optimal revenues for those constraints is just their sum. So natural linearity property defined on this revenue operator on the allocation constraints. Okay, and this is not a coincidence for the uniform case. It's actually a fact. For every revenue linear case, revenue linearity implies orderability. So you'll always get this convenient ordering property if you have revenue linearity.
And the converse?
No. And the converse, let's see. Let me not say anything right now.
So Jason, I think some of these is some constraints.
Yeah, think of it as taking a convex combination instead of a direct sum like I've written here. So write y hat as the convex combination of two other allocation rules. And then my first one will be the coefficient of the first one times this first one. And this is the coefficient of the second one times the second one. Okay, so think of it as convex combination. Yeah?
The y hats are interim constraints.
Yes. Okay, I now want to give you the ex ante reduction. Okay, in particular, I'm going to show you that revenue linearity is going to imply that the Meyerson-Bulow-Roberts mechanism of marginal revenue maximization is just going to extend naturally to give you the optimal mechanism for these settings. Okay, so to define marginal revenue, we've for every ex ante constraint q hat, we've solved the ex ante pricing problem. Let's define R of Q hat to be the revenue for every Q hat. And then this will define a revenue curve, which is going to be a nice, concave function. I can take its derivative and let that derivative be the marginal revenue, and call the derivative the marginal revenue. Okay? And then the theorem that you will recognize from the single-dimensional theory is the following, that the optimal revenue for a constraint y hat is just equal to its marginal revenue, meaning the revenue is equal to the expectation of, if I were to view sort of marginal revenue like as a virtual value, I get sort of the surplus of marginal revenue. This theorem has the assumption of revenue linearity. I should have written it here.
Y hat is interim?
Y hats are always interim, yes. Yes. Y and Y hats are interim allocation rules. Okay, so here's the proof. So another way to reinterpret what this revenue from the ex ante pricing is actually the revenue of the interim mechanism with a constraint that steps from 1 to 0 at Q hat. Okay, so if I had Y hat is equal to this, I would get optimal revenue equal to R of Q hat. Okay? And then any allocation constraint Y hat can be viewed as a convex combination of reverse step functions. Coefficients are the negative derivative of the allocation rule. Okay? So then, using revenue linearity, I can write the expected revenue as, well, this is just the convex combination of a whole bunch of other step mechanisms. What is its revenue, therefore? Its revenue is the probability that I run the Q hat mechanism times the revenue of the Q hat mechanism, which is this. Okay? And that expectation you can view as an integral, and you can integrate it by parts to switch where the derivative is to get the marginal revenue definition. This is exactly the analysis you would have done if you were doing the single-dimensional case. Yeah?
Right. Optimal revenue, what are you optimizing over?
Great question. Let's remember that. So the interim pricing problem. For every allocation constraint y, I want to find a mechanism, every allocation constraint y hat, I want to find a mechanism y that is constrained by that mechanism via some resampling transformation sigma. Okay? Over all such mechanisms that satisfy this constraint, that's your question. Okay? And I gave you some examples of that, where here's was what I did. When I gave you allocation constraint y hat, you came up with this y. Right? When I gave you this allocation constraint y hat, the same allocation constraint y hat, but I had public budget, you gave me this other y.
So are there so there are prices also?
Yeah, so I've just written this in terms of the allocation rule, but there are prices that make it all incentive compatible because this is over single agent mechanisms that are incentive compatible. Okay, but those I don't have to talk about here. I'm just talking about the allocation control, and you want to maximize the revenue that comes from that. That's implicit in that optimization question.
All right, just make sure I understand. So you are optimizing both over sigma, and then for a fixed sigma, you still have to optimize over the mechanism. It's not that for a fixed sigma, there's...
That is correct. But I would view it slightly differently as when you optimize y, there'll be an implicit sigma that comes out of it.
So,
in fact, I would just write this constraint as your constraint and ignore sigma and just optimize with this constraint. Okay, and you'll get sigma for free.
So for every sigma, there is an IC mechanism.
Yeah.
So you can reshuffle types in whatever way.
Yeah. That's not so exciting. Because for every sigma, the allocation rule is monotone. For every monotone allocation rule, I construct a mechanism. Okay, so that's the proof that optimal revenue is always equal to marginal revenue. Yeah.
So this convex combination of allocation rules, is that coming out in the expectation over the quantiles? Is that what's happening here?
Yes. So the point is, I have a monotone decreasing function. Okay, I can write every monotone decreasing function as a convex combination of functions that step down, right? Where the probability on this is the negative derivative of that function at this point. Okay, so this first part of the equation is just rewriting the revenue linearity equation, where the terms in it are the allocation rule weighted by the probability that I have that allocation rule in there.
So the analysis of the previous slide, this is for single dimensional setting?
No, this is for any setting that's revenue linear. I should have written that here. So for revenue linear settings, this holds. The only assumption I used was revenue linearity here. Okay.
So the allocation is single dimensional, right, for given bidders. It's the preferences.
So I'm keeping track of the allocation as a single dimensional quantity here.
So I guess I'm going. So your previous claim that the allocation is monotone. When you look at it in the quantile space, there's a mapping from the multidimensional preferences to this quantile space.
Uh-huh.
Now, if you reshuffle that in whatever way.
You're right. You don't get it at IC, but I'm mapping quantiles to quantiles in my construction, not types to quantiles. But you're correct that when you solve this problem, you implicitly have to figure out the mapping from types to quantiles, because any mechanism will map types to quantiles, as I defined on the previous slide. There induces a mapping. So you must have figured that out.
Okay. So your problem here is I give you this y hat in quantile space. You have to figure out the mappings.
Figure out. Look, so every mechanism induces an allocation rule, right? So over all mechanisms, find one that induces a rule that satisfies, let's forget this, just this property. Yeah. Yeah.
So there's the implicit assumption that I always get my most preferred object if I get one.
I have an IC assumption, which means this mechanism basically looks to you via the taxation principle like a menu. You always choose your favorite outcome. Okay, that might not be your favorite item if it's priced higher than your other item in some mechanism, right? In the unit demand example I was talking about, it will always turn out to be that way, but you only notice that once you solve the single player problem completely, which I haven't done yet. I'm going to do tomorrow. Okay, so that's a detail of the single player problem, which I don't want to talk about today. We'll talk about that in great depth tomorrow. Items or whatever, and incentive compatibility constraints. Okay, good. So let's now say, what is the optimal multi-agent mechanism under the revenue linearity property? And you can define the marginal revenue mechanism for orderable agents. And remember, every revenue linear agent is an orderable agent because revenue linearity implies orderability. So step one is you map agent types to quantiles via the ordering that's implicit in the single agent problems. Okay, so this is a type profile, so it's all the types of all the players. And you get a quantile profile by this mapping. Then I'm going to calculate the marginal revenues of all of the agents at the quantiles I get from this mapping. Okay, and then I'm going to serve the agents to maximize the total surplus of marginal revenue. I find the xi's that are feasible and maximize the sum. For a single agent, I just choose the guy with the highest positive marginal revenue. Okay, and finally, to find the outcome and payments for each player, I'm going to look at how much they could increase their quantile, meaning go to lower types, and still be served. To find a critical quantile, which is the quantile at which they couldn't increase it anymore. Okay, that critical quantile has a mechanism that's defined by solving the ex-ante problem for that quantile. That player sees the mechanism that's the ex-ante mechanism for that quantile. So now to answer the question of why do we care about these mechanisms, those actually appear in the construction here. You're going to then use that ex ante mechanism. And notice that this player will always actually be served by this mechanism.
Jason, is the critical quantile the one in which your risk probability falls all the way to 0, or it falls at all lower than what your current probability is? I'm not sure this critical quantile is.
That's a great question. So, because implicit in that question is that these players might be served with probabilities. But actually, if once you've done this, x is going to be 0 or 1. Okay? And that's going to come out. So in fact, a property we had in the single dimensional setting, which was the allocation, who wins and who loses, it's deterministic, is maintained in this setting. It will always be 0 or 1. Okay? Okay, so the theorem is this mechanism is optimal. How do you prove this? Well, we pointwise optimize marginal revenue, and marginal revenue is equal to optimal revenue always by the previous theorem. So we have to have optimized revenue. Now, is it incentive compatible? Well, the revenue curves are concave, so the marginal revenue curves are monotone. So these critical quantiles I needed here exists, and this is IC, which is the standard proof that you would prove this mechanism if you were Roger Myerson. Okay, so I want to return to my example, which was revenue linear, which is the uniform 0-1 squared case. So the red-blue car types ID uniform 0-1, and reinterpret what this marginal revenue mechanism is, and we'll see we get the exact same thing I said I would get at the very beginning. Okay, so again, the uniform 0-1 agent is revenue linear, and the revenue curve R of Q comes from posting a price square root 1 minus Q hat. Okay, so it looks like this. Okay, you can plot out what the revenue you get from this is. If you post this price and you're selling with probability Q hat, your revenue is Q hat times the price you get. So Q hat times square root 1 minus Q hat. That's the revenue curve, which has this form. And you can see it's optimized at Q hat equal 2/3. Okay. How do we map types to quantiles? Well, by strength. And remember, the ex ante mechanisms are always sort of just posting higher and lower uniform prices. So the stronger players are the ones that have a higher value for their favorite item. Okay? And so what is that? So given your type is T red, T blue, then your quantile is 1 minus the max of T red, T blue squared, which is how you can convert. If your type was here and T max was here, you convert that back into probability space by asking how many people are stronger than you. Okay. So now I want to maximize marginal revenue. I have an IID setting. So as usual, the values of marginal revenues don't matter. It's just the ordering matters. And so we just care about who has the highest marginal revenue. And the person with the smallest quantile has the highest marginal revenue. Right? And they're the person with the highest favorite item coordinate. Okay? So serve the agent with the smallest quantile less than 2/3, and they start to have negative marginal revenue. And so that's serve the agent with the highest maximum value, charge the second highest maximum value, or reserve square root 1/3. The same mechanism I said would be optimal on the first slide. Okay. And so revenue linearity implies this mechanism is indeed optimal. Yeah.
Can you remind me how you knew this was revenue linear, and more generally, how you know in the setting of revenue linear? Or how you what property?
So I didn't give you a general method for determining whether a setting was revenue linear. I will give you a general method tomorrow for determining whether a setting is linear. So I'll give you two answers. One, you can solve a program to check revenue linearity, a mathematical program. You can just plug it in and ask if it's revenue linear. It's not a very nice answer. The other answer is you could observe the structure of the interim optimal mechanisms, which is what we did today. So we saw this interim optimal mechanism for the unit demand case. And if you look at this allocation rule, what is it doing? It's gradually increasing probability as you get higher coordinate for your favorite item. Okay? What were the optimal ex-ante mechanisms? They were just posting a uniform price. So you can implement this allocation rule by taking a combination of those ex-ante mechanisms. Therefore, it's revenue linear. Okay?
That didn't depend on the allocation constraint.
Exactly, and that's the point. So the point is it will always look like this for any allocation constraint. It'll have this exact same reserve price, and it'll be greedy up to that reserve. So the curve will match the thing up to the reserve, then it'll drop to 0. Any more questions?
Settings that are not linear.
Okay, so I am out of time, which means I'm going to push the discussion of the general setting to tomorrow when things are not revenue linear. Okay, but so to conclude for today, we saw 2 examples, unit demand, public budget, and unit demand. They behave very differently when I look at their single agent problems. And the structure of the behavior of the single agent problem for the unit demand case was especially nice, which allowed us to use very simple marginal revenue tools to understand what optimal mechanisms are. Okay, so next time we'll see how to solve for optimal mechanisms when we don't have this nice structural property. In particular, we'll work out the optimal mechanism for the public budget example. I'll do a bunch of other things as well.